In this video, we're going to talk about properties of rational functions. Say, what is a rational function? You may be asking yourself, or I don't know, the screen you're watching this on, but a rational function, if you don't know, is defined as this, which is maybe not the most helpful thing, but it's essentially a function where you have a function in a numerator and a function in a denominator. So it creates a fraction. So most likely you'll have an x in the top and an x in the bottom, but at minimum you'll have an x in the bottom, which creates some interesting things. Here we have examples of rational functions and their graphs. So this one maps to this. Pretty simple, pretty nice. And then these two map to these two. We got lots of red dotted lines here, and those are asymptotes, which we will cover in just a moment. One major component to rational functions is finding the domain. So essentially where the x values exist and where they don't. So we've talked about domain quite a bit, but in a rational function it's pretty obvious. It's whatever makes that denominator 0. And we'll do a couple examples to figure out what our domain's going to be. In this instance, we've got 2x squared minus 4 over x plus 5. I don't care about the top for the domain. All I care about is what makes the denominator 0. So our denominator is in factored form, can't do much with it, set it equal to 0, and x is equal to -5 is the only place our domain will not exist. So in interval form and in set builder. And let's jump to our next example. We've got 1 over x squared minus 4. So this isn't in factored form, so let's factor it first. Luckily, I know my perfect square binomial factor, so that's going to be x plus 2, x minus 2. So that gives me -2 and 2. Those are the two values, lots of 2's. Those are the two values where my domain will not exist. So again, interval, set builder. And for this example, we've got x cubed over x squared plus 1. Now, if you happen to know things about perfect square binomials, you could look at this denominator and right away tell me that there is no break in the denominator because I cannot factor x squared plus 1 the way I could factor x squared minus 1. Because remember, it's the difference of two perfect squares that I can factor. So this one, I don't have any restrictions to my domain. It's a beautiful thing. It'd be all real numbers. But let's say that I didn't happen to know that. Let's try to set this equal to 0. So what I would do is set x squared plus 1 equal to 0, subtract 1, get x squared is equal to -1. You know, take the square root. Great. X would be equal to the positive negative square root of -1, which isn't real. Cool. So that would give me plus or minus I, which is great. I love me some imaginary numbers. But there's going to be no restrictions to my domain. There's nothing that x can equal that will make this thing 0. And that means my domain is all real numbers. So now I want to do one last domain example where I factor both top and bottom of my rational function fraction. So when I've factored x squared minus 1, I get x plus 1, x minus 1. And then in the denominator, I can't really do anything with that. It's still x minus 1. But notice I have the same factor on top and on bottom. Now you may be tempted to cancel that and tell me, wow, no denominator, all real numbers. This thing has no restrictions. So factoring it and finding things that are in common on top and bottom do not impact the domain in that same way. They will impact something else, which we'll talk about again momentarily. But the domain is from the original function. So even if you can cancel this out, x minus 1 over x minus 1, don't. Not for domain, at least. So let's find the domain of this one. So that means the domain x minus 1 is equal to 0. X is not going to be 1. That's the thing that's going to zero out our original denominator. And so that's our domain. We're just going to skip over 1. And here we have a very important and very interesting part of rational functions, and that are the asymptotes that are created by rational functions. So, as we saw in the domain, there are many places that our domain will not exist. So, when you have a rational function, these are some shortcuts you can use. If you set the top equal to 0, those will give you all the x-intercepts. And if you set the bottom equal to 0, those will give you all your vertical asymptotes. But it might also create holes. So domain is affected by both vertical asymptotes and holes. So if there's a hole and vertical asymptotes, you'd write them all in your domain because domain will skip over both. So here's how you tell the difference between, is it a vertical asymptote or is it a hole? So like we did in the last example, once we factored it, we had the same factor on top and bottom. In this example, in factored form, I have the same factor x minus 1 on top and bottom. That creates a hole. So if you think about it, if the top set equal to 0 is your x-intercepts and the bottom are vertical asymptotes, how could you have an x-intercept on the top but then an asymptote going through that same x-intercept? So that creates a hole in our function. So it would be at 1. And any other functions, or factors left over in the denominator that are not shared in the top or the numerator, those are just our vertical asymptotes. So x plus 4 is not in the top, but it is in the bottom. So that's going to create an asymptote at -4, but a hole at 1. So if there are vertical asymptotes, there's got to be horizontal asymptotes, or maybe you weren't even thinking that, but there are. There are likely horizontal asymptotes. And they don't come from the factors. They come from the degree on the top and the bottom of the function. So remember, a degree is the highest power, the highest exponent a polynomial can have. So a rational function has a polynomial function on the top and a polynomial function on the bottom. So we call this n over m. So if the degree of this is n, then the degree of the one on the bottom is m. You can call them whatever you want, but these are the rules that create our horizontal asymptotes. So here are the rules for horizontal asymptotes. If your top degree, your n, is less than your bottom degree, making a proper function of sorts, so 1 over 2, 5 over 7, 12 over 13, whatever it is, your horizontal asymptote is going to be the x-axis, or y equals 0. So that's if the top is less than the bottom. If they're the same, where n is equal to m, then you take your a value, so the coefficient in front of that highest degree, and the coefficient in your bottom, and that's going to be your horizontal asymptote. So if this was 1 and that was 2, it'd be y equals 1/2, for example. So the only other case you can have is if the top degree is larger than the bottom degree. So if the top is larger than the bottom by 1, you'll have what we call an oblique or slant asymptote. So these two asymptotes for these first two rules are horizontal lines. They have a slope of 0, straight across. But an oblique or slant will have a non-zero slope. So it could be positive, could be negative. So if this was 2 over 1, 3 over 2, 4 over 3, etc., greater on the top by 1 than the bottom, you're going to divide, preferably using long division of polynomials. But if the top is greater than the bottom by more than 1, so if there's a difference of 2, 3, 4, whatever, then you won't have any horizontal, slant, or oblique asymptotes. And if you don't know by now, I certainly love lots of examples. Let's get started. So let's find the asymptotes and possible holes of this function. So we've got x plus 3 over x minus 1. So here we have our vertical asymptote, x minus 1. It's going to give me x equals 1. And then now I need to compare the degree on the top and the bottom for my horizontal asymptote. So n is 1, m is also 1, which means that they're the same value. So I plug it into my y is equal to a over b. So the coefficient here, which is a, is 1. Same deal with b. So that's going to give me y is equal to 1 as a horizontal asymptote. So they're both 1. And here's the graph of this function in green. And then the horizontal is at y equals 1, and the vertical is at x equals 1. Look at that. All right, so let's look at this one. X over x squared minus 4. First thing I'm going to do is factor that denominator. So I factor to get x plus 2, x minus 2, so that gives me my vertical asymptotes at x equals -2 and +2. No, I don't need to do anything with the top, so there's no holes here. There's nothing else I can do factor-wise. And so now I move on to the horizontal asymptote. So the degree on top is 1, the degree on the bottom is 2. So n is less than m, so that gives me an automatic horizontal asymptote at y equals 0. So here we've got our function with our asymptotes. So I've got 3 pieces here because I've got 2 vertical asymptotes. I like to think of vertical asymptotes as kind of the electric fences of the graphing world, because the function will not cross over a vertical asymptote. Ain't gonna happen. But horizontal asymptotes, your function can cross over them. Usually your horizontal asymptote only affects one piece of that rational function. So if you noticed our horizontal asymptote at 0, it kind of directs this piece and this piece, but it cuts right through the middle one, which is pretty standard, pretty common for horizontal asymptotes. So vertical asymptotes, your function will never cross through them or touch them. But horizontals, that can happen. All right, we've just increased our spice level with our examples. So only because I need to factor the top and the bottom. So let's do that and then see what we get. All right, in factored form, in the numerator, x plus 3, x minus 3. In the denominator, x plus 7, x minus 3. So we've got the same factor on top and bottom. So that means that x minus 3 is going to be a whole. So x is equal to 3 is going to be a whole, and our vertical asymptote that's left over is at -7. So one extra thing you can do for the whole is to find the coordinates of where that whole would be. And so this is where the fully factored and simplified version of the equation is useful. So if I got rid of this, I have to, right? Because if I plugged in 3, it would zero out the top and the bottom, which is the whole point of why it's a whole. So if I get rid of these and I plug in 3 for the remaining x's, I would be at 3 plus 3 over 3 plus 7, 6/10, which is 3/5. So the whole's coordinates, which are useful when you graph it, is 3, 3/5. So now let's find the horizontal asymptote. So our n value is 2, our m value is 2, so that creates a horizontal asymptote of a over b, and both a and b are 1, so our horizontal asymptote is at 1. So what we're looking for in the graph is a whole at 3/5, vertical asymptote at -7, and a horizontal at 1. And here we have it. So vertical asymptote, -7, horizontal at 1, and I've got a whole at 3, 3/5, which is 0.6. This is the last example, I promise. Okay, let's do 2x squared minus 5x minus 3 over x minus 6. So luckily we only need to factor the numerator. Here we go, 2x plus 1, x minus 3 all over x minus 6. So there's no factor that's the same on top and bottom, so I don't have any wholes, which is lovely. So let's find our asymptotes. All right, we've got one vertical asymptote at x is equal to 6, and now I move on to my horizontal. I got 2 over 1, so that means that n is less than m by 1. So that means I have an oblique asymptote. So that means I actually need to divide this top function by this bottom function. So in this instance, I'm going to do it with long division of polynomials. So let's check out how to do that. So the way that I set this up is much like how I would set up synthetic, and you can use synthetic as long as this x value right here has a 1 in front of it. That makes it a lot easier. But I want to show you long division of polynomials. So I've got my top written out, all the terms, all the x's, all the coefficients, and then my bottom term out here. So my goal is to figure out what has to multiply by x to get this first term here. So this is an x to the first. In order for it to become 2x squared, I would multiply x by 2x. And then in order to find what goes beneath so I can subtract, I multiply this 2x by each of these terms. 2x times x is 2x squared, and 2x times -6 is -12x. So I stack them underneath their matching variable and exponent. So I'm going to subtract these and see what I get. So 2x squared minus 2x is nothing. That's the whole point of putting the 2x up there. It takes away that first term. And then -5x minus -12, so that becomes -5 plus 12. We get positive 7x minus 3. So for my next term, I have to figure out what x needs to be multiplied by to get 7x. So that's just going to be a positive 7. So 7 times x gives me 7x. 7 times negative 6 gives me negative 42. 7x minus 7x gets rid of that term. Negative 3 plus 42, because a negative times a negative, is 39. Now, the beautiful thing about dividing a function is that once you have an equation, so where you have something with an x and something with a constant term, it doesn't matter what the remainder is. It doesn't matter. It's so insignificant. It's so small. It doesn't really change the oblique or the slant asymptote. So if you have a remainder of 0, beautiful. If you don't matter. So once you get to this point, this is my oblique asymptote. So it's going to be 2x plus 7. So it's going to be a positive slope that will dictate where these pieces of this function will go. And here it is. Vertical asymptote at 6. And then here's our slant asymptote, 2x plus 7. Do you see how it creates like this curve going that way and that curve going that way? So that happens only when you have a power that is greater by 1 than the power on the bottom. And if you like summaries of rules and things, screenshot it or don't. Your choice. And that's going to do it for this video. Me and my little doggo pal are going to ride off into the sunset. Thank you for watching.